Okay, so at some point, we will see a good example, a very important example of the isomorphism theorem, where we construct the homomorphism between the group known as SU2, which is the group of rotations in quantum mechanics. So, and the group SO3, which is the group of rotations in real space, which we will discuss today. And we will see that in that case, K is going to be a non-trivial. It'll be Z2, and therefore we will find that there is an isomorphism between SU2 over Z2 and SO3. Okay, so this will be an example of the isomorphism theorem, and we'll see that we'll construct this very, very carefully and very, it's a very important example. And we'll also do another one where we will construct a homomorphism between what is known as another group called SL2C and a group which is also very important in physics called the Lorentz group, or SO1, 3. Okay, so we'll come to these, to this stuff in, and I'll remind you of the isomorphism theorem at that point. Okay, so I want to move on to the next topic, if you guys don't have any questions or comments at this point. All right, so next I want to discuss continuous groups. But before delving into and representation, but before we get into this, I want to have more of a like a informal, hand wavy sort of example-based discussion. Okay, because this is really where the kind of it also sets up the motivation why physicists, groups consider groups so important. So let's start with what is known as the rotation group. Okay, so the rotation group, and let's take the rotation group in 3D. In three-dimensional Euclidean space. Okay, let's write that out. So our space is more or less Euclidean because we are far away from any very strong gravitational field. I mean, we are in one, but it's still approximately Euclidean. So, consider a position vector. Say R. Okay, so R can be written as xi, yj, zk. So, we have some reference frame like this. That's the z-axis, that's the y-axis, that's the x-axis, x, y, and z. And the position vector is something like this. And the coordinate of this point is x, y, and z. Sorry, I'm using the same letters for the axes and the coordinate of the points. Okay, so now if I make a rotation of this vector, then see what happens. But before we do that, let's rewrite this vector as a matrix. So let's take this vector and write it as just R, a column matrix, and its coordinate of those points as x, y, and z. Okay, so these two guys have the same information. So the norms, so the norm squared, or the Euclidean norm of R is, let's call this R squared, and that's going to be in matrix notation. What will this be? Can someone tell me?
R transpose R.
This will be R transpose R, and that is x squared plus y squared plus z squared, right? Do we have any questions? Okay. Now, consider, the set of linear transformations of R, such that R squared remains unchanged or invariant. Okay, so that means R will get transformed into some new column vector. Let's call it R prime. And it's a linear transformation, so that means that there will be some linear operator, say O, acting on R, right? So since we are representing small r, we are representing small r as a column matrix. How should we represent the linear operator O? So this is also a column vector, a column matrix, three-component column matrix. These are three-component column matrix. Then what should this O be?
3 by 3 matrix.
Yes, to be a 3 by 3. It should be a real matrix, right? Because we know that both the entries of R and R prime are real. Okay, so in general, O should be a real matrix, right? 3 by 3 real matrix. So our condition that this linear transformation preserve the norm of R means that we can write R prime squared is equals to R squared. Or in other words, R prime transpose R prime is equal to R transpose R, right? But if I use this equation now, on the left-hand side, I get O of R and O of R transpose. Sorry, transpose, not prime. That's equal to R transpose R, right? Now we know that when we transpose two matrices, what happens to them? A product of two matrices, what happens?
Order changes in the transpose and each of the matrix transpose.
Right, so this is what happens. So that means that we can write this guy as R transpose O R. And here it's R transpose R. But R is an arbitrary position vector. So if this equation is to be true for any arbitrary R, then it should be true that O transpose O, the linear operator, its transpose and O, the matrix multiplication of O transpose and O must be the identity matrix, right? Okay? Is that clear? All right, so that means that the transpose of the matrix O is equal to its inverse. Such matrices are called orthogonal matrices. So O is an orthogonal matrix. Okay? Now comes an interesting statement. So that the set of all matrices that satisfy this condition, or I should say all real matrices that satisfy real 3x3 matrices that satisfy this condition, they form a group. And this group is known as O3, or the orthogonal group of 3x3 dimensions. Known as, let me just rewrite this because it's known as the orthogonal group O3. Okay, so let's just show that this is indeed a group